to go over some of the announcements. I think I've hit most of these before, but just in case, on the administrative calendar, this week is the last week of the first mini-term. That means midterm is coming up as in immediately, like this weekend sometime. And classes begin for second mini-term next Monday, okay? The fact that midterm is happening and you're in great shape and one of the others is in great shape. The other one is not yet, but hopefully it'll get there. We have to do a midterm progress report. All students who are not passing at midterm, we have to report those so people will get in touch with them, see if they need tutoring or whatever. You're in great shape, and at least one of the other guys is. Okay, so I'm saying this mostly for the other one. Please get something to me before Wednesday of next week. The first test, the paper, research paper, anything to me before Wednesday of next week. That's about all I can see that needs to be covered there. The volleyball team has a match versus Snead State tomorrow. It's a home match, so they'll be hosting them. Birmingham West Campus, Arthur Shores Fine Arts Building, which is also the gymnasium. That will be occurring at 6 o'clock. I'll be in class, so I won't get to see it, but they will be playing at 6 tomorrow. Scholarship Summit is coming up tomorrow and Thursday. Okay, tomorrow and Thursday. Tomorrow is on the Birmingham campus in the new Academic Success Center in the auditorium from 1 to 3. I think I've read all these to you before. And then the next day, Thursday, it'll be on this campus from 1 to 3 in the faculty staff dining room, which is just next to the cafeteria. Lots of schools will be here, by the way. And the NASA Community College Aerospace Scholars Program will be taking applications through October 16th, which is next Wednesday, I think it is, isn't it? I believe so. So please, if you're interested, get those in by then. All right, now, my work study student has been doing a great job, going through old papers and changing files. We have to keep papers for up to 3 years, and then we cycle them out, the next ones in. She's been doing a great job doing that, but for some reason, and she knew that everything on this side of my table was current classes, she got my linear algebra stuff and moved my marker pages around, put them to the front of the book, not where I had them, and then also put in one stack to file the research paper and took my resource book and put it somewhere else, and I can't find any of the papers, any of them. So I may not be able to return your first test because I don't know what she did with it. And she said, oh, it's here somewhere. So, okay, well, I need them because not only that, subsequent tests, I don't know what she did with them. They're not here. They were in a stack by itself, not bothering anyone, and she did something with them. So when it gets close, and it is close to the next test, I'm going to have to, if I can't find it, well, hopefully I have it on my flash drive and I can just make another copy, and then I'll have to make another key and all that kind of stuff because she did away with everything, okay? And I don't know why. All right. That's my sad song. So let's go to the current slide. And so I wanted, where did you have us leaving off last time? I'm guessing it's the bottom of page 66, example 5. Is that it, or had we already done that? Maybe the top of 68? I don't remember doing that one for sure. It seems like maybe we did the properties of inverses, didn't we? We did that. So we did the discovery at the bottom of 67? I think we did, yeah. and then we're ready to do example 6 at the top of 68. Is that right? Does that seem right? That it? All right. So that's where we're beginning today. No questions on anything we've done so far? Okay. So let's talk about the inverse of the square of a matrix. Now, we just did some properties of inverse matrices, as in the, well, actually theorem 2.8 did cover this, okay? The inverse of the square of a matrix. Number 2 is basically dealing with this one. So let's do it. Compute, let me get my pen set up. Compute a to the minus 2 in 2 different ways and show that the results are equal. So here's a 1, 1, 2, 4. Okay. Now, we need to compute a to the minus 2 different ways. Now, how would you suggest we do it? One way. Pick a way anyway. Okay, you're going to do a squared first. So a squared, I'm just going to write it like this, would then be a times a. 1, 1, 2, 4. And certainly you can do that, and it will produce a square matrix, 2 by 2. So give me the first entry. Yep, 3, is that right? Got it. Next. 10. 18. Got it. So there's a squared. What would you do next then? Second. Okay, yeah, okay, you're telling me exactly the steps. So the determinant of this, let me just do this. Here's the symbol for it. I don't know if you knew this or not. 3, 10, 5, 18. The straight lines like this that look like absolute value bars, that means determinant. And what would that be? (54) minus 50 is 4. Is that what you said? Got it. All right, what do you do with that? Okay, I couldn't hear all that. Say 1 over 4. Okay, and then what would be the matrix you fiddle with here? (18) up here with a 3 down there. -5 and -10 right where they sit. Okay, that is a to the minus 2 done one way. Okay, what would be a to the minus 2 done another way? Inverse of a. So let's do a inverse. Okay, and what would you do first? Okay, the determinant of a would be determinant of 1, 1, 2, 4, and that would be 2. So the inverse would be 1/2. Let me clean up a little bit. Okay. Pretty ugly one there, but I guess we can live with it. Of what? 4, 1 on the diagonal. -2 on the other diagonal. And then what will we do with that? Okay, so that'll be multiplying by another 1/2, and then by another 4 minus 1 minus 2, 1. So let me just get the 1/2s together and make those a 1/4. That looks okay. And then these two, if you multiply them together, will produce another 2 by 2. And what will that become? Right? Which is 18. That looks good. Next. Which is? That looks good. Next. Or negative 8. Negative 10. That's looking good. And the last one will be 3. And that's it exactly. So you have calculated a to the minus 2 two different ways. You first squared a and then took its inverse. And secondly, you took the inverse of a and then squared it. And they both indeed give you the same, identically the same answers. Okay? And why they did this, I'm not sure, but we'll do it that way. They wrote them both without a fraction in front, which really is messy, but we'll do that. This one would be, and they're the same thing, that would be 9/2, right, minus 5/4 minus 5/2 and 3/4. And of course the other one would be exactly the same. 9/2 minus 5/4 minus 5/2 and 3/4. And let's see if that's what they got. 9/2 minus 5/4 minus 5/2, 3/4. Got it. All right. Any questions on that? Good deal. Well done. So let's move to Theorem 2.9, the inverse of a product. Now, we've just done, on our discoveries, we've done this before. So let's write it out in a theorem form. If A and B are invertible matrices, stands for invertible matrices, of order n, so they've got to be the same order. Of course, that means they're square. To be invertible, you have to be square. Then, that tells you that AB is also invertible. No question about it. And what that inverse is, AB inverse, make sure I wrote it that way, is what? You remember? From our discovery that we did last time, is equal to B inverse times A inverse. You reverse them and invert them separately. Okay. Now, to show that that is an inverse of AB, okay, that is an inverse of AB, what we can do, and these are sort of fun little proofs to do. I know you love doing proofs, so you probably eat this up. AB inverse equal to, well, wait, okay, sorry. We're trying to show that the last thing is the inverse, so let's not assume that it is. Okay, so let's take the last thing we've got there, and that's B inverse A inverse. Okay, and then that means that if you take this and multiply it by AB, on either right or left, it doesn't really matter, see what you get. Well, if you recall, it doesn't matter the order you do the multiplication of matrices, just do them. So let's do the inner two first, and that would be A times the I matrix times A inverse. Well, A times the I matrix is just A, and that times A inverse is going to be the identity matrix of that size n, okay? Both of those have to be I sub n. Well, let's see if it works the other way. If we did B inverse A inverse and multiply that by AB, what happens there? Do the same thing. Group the middle two together, and you get B inverse times I sub n times B, and that gives you B inverse, because any matrix by its same size identity matrix is going to be itself, times B is sure enough I sub n. So yeah, pretty easy little proof to do. Okay? Now, bottom of the page there says theorem 2.9, which is one we just did, states that the inverse of a product of two invertible matrices is the product of their inverse taken in reverse order. That can be generalized to include the product of several invertible matrices. Let's say A1 times A2 times A3 dot 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 times A sub n. Okay? And take all of those need to be invertible matrices. So the product of them all has to be an invertible matrix. And then the inverse of that would be A sub n inverse times A sub n minus 1 inverse times A sub n minus 2 inverse dot 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 all the way down to A sub 3 inverse times A sub 2 inverse times A sub 1 inverse. And you can prove those by, again, multiply them together, and these two become the identity matrix, the next two all the way down. So yeah. So let's do example 7. We will need more room for that. Find AB inverse for the two matrices. Here's A, 133, 143, 134. B has to be the same size, 123, 133, 243. Okay? It says find A, B inverse for those matrices. All right. There's, again, two ways you can do it. What would be the two ways? We're looking for A, B inverse. AB, product of AB inverted. Two ways to do it. Second? I think I would too. And I think that's a smart way to do, because if you do that, then you just got one matrix then that you have to do the inverse of. What was the other way you could have done it? Yeah, you do B inverse then A inverse and multiply them. Well, there you have two 3x3s you have to invert. This way you only have to invert one. And you still have to multiply the two matrices together, so this comes out a step or two easier. So let's multiply first. Of course, the AB, the product of those is going to be a 3x3. All right, let's do it to it. Ten. Next. You're giving an answer, I can't hear it. Okay, now I got 20. Are you going across or down? Across. Okay. I may have done it wrong. Is it 9?
Yeah, because it's 2 times 1 and 3 times.
Oh, you're right. You're right. I went the other way. I mean, not the other way. You're right. I did 2. I don't know where I got an 8 there. Okay. 2 plus 9 is 11 plus 12 is 23. Is that right, you said? Okay, 23. Got it. Next. $21. Got it. Next. $11. Got it. Next. $26. Okay. And $24. Is that what you said? Yeah, that's what I got too. Next. Did you get 12? Goodness gracious, why am I coughing so? Did you get 27? Yeah, that's what I got too. Just coughed when I was writing it, and it came out ugly. Okay, and last. 24, you said? Okay. So that gave us AB. What have we got to do next? Inverse. Now that's no easy way like it is with a 2 by 2. What do we have to do? No, yeah, you can't, there's no little rule like that. What you have to do is write down the identity matrix, and that is 0, 1, 0 and 0, 0, 1. And now we're going to do a row reduction. Now, in my mind, the best way to do this one, at least to start with decimals, okay? Because what the first thing you got to do? Divide by 10. So that's going to make everything a decimal number. I think we're better off that way than we are doing fractions. Now that's just my opinion, but let's see what we can do. First we'll row 1 divided by 10 is the new row 1. Okay, so this will be 1, 2.3, 2.1, 0.1, 0, and 0. You buy that. Okay. Now, what you going to do next? Okay, 11 row 1 plus row 2. I'm writing it in the wrong place. 11 row 1 plus row 2. No, minus 11 row 1 plus row 2 is a new row 2. Okay, let me clean that part up a little bit. Wrote it in the wrong place. All right. And do it to it. Now we're using this row 1, not the row 1 above it. Okay, that row 1. That's why I wrote it over there. I said, yuck, I'll need that space later. So let's do that. So that'll be 0. Okay. Now the next one gets a little messy. So I'm wondering now if we really wanted to do it. But let's do it. If you got a calculator, do it with the calculator and let's see how it works. Yeah, it's 23 times 23 would be 4. Is it 59? Is that right? Yeah. If you're doing minus 11 times 2.3, I think will be. No, I'm sorry, I said it wrong. I'm sorry, I was squaring it. Okay. It was 23 plus 23 is 253. 23. Yeah, 25.3. Okay, minus 25.3 plus 26 is minus 0.7. No, positive 0.7, right? Yeah, it wasn't a minus 2.53, no, 25.3 plus 26. You're adding. Yeah, I think that's right, isn't it? Negative 25.3 plus 26 would be a plus 0.7. Ooh, that came out better than I thought it would. Now let's do the next one. Minus 11 times 2.1 will be minus 223.1, right? Minus 323.1 plus 24 is 0.9, I think, isn't it? Okay. The next one's not too bad. Negative 1.1 plus 0 is negative 1.1. Right? And then I can do maybe the next one. 1. Right? And 0. So far, decimals are doing us okay. All right. Next. Negative 12 times the new row 1 plus row 3 will be the new row 3. Okay? Negative 12 times 1 is negative 12 plus 12 is 0. You knew that had to be. All right. Negative 12 times 23. This is where calculators come in handy. Do you have one? Okay, let's do it. No, times 2.3. I was looking at the wrong one. Negative 12 times 2.3. Second? Okay, and we're adding to that a 27, so that'll be a negative 0.6. Okay. Then do a negative 12 times 2.1 and add to that 24. Negative what? 1.2. Okay. Then I think I can do this one. Negative 12 plus 0 is negative. Whoa. No, Negative 1.2 plus 0 is negative 1.2, right? And 0 and 1, right? Okay, things are going to get a little messier now. And do I hear a suggestion on your part? If you divide this one by 0.7, which would be my first non-thinking reaction, then that's dividing that by 0.7, which is going to be a mess. Dividing that by 0.7, which is going to be a mess. Even dividing that by 0.7 is going to be a mess. And dividing that will be okay. That will be 0. But if you divide this one by negative 0.6, that will come out nice. That will come out nice. That will come out nice. And that won't hurt. I mean, it'll be bad, but it won't be as bad as the top row of the second row. So I'm thinking, let's flip those two rows and divide by negative 0.6. What you think? Okay. So I'm going to leave the top row alone. 1, 2.3, 2.1, 0.1, 0, and 0. I sure took up too much room for that one. And then the new second row will be 0, 1, 2, 2, 0, and it's a mess. I'm just going to put negative 1 over 0.6. Actually, what I might like a little bit better is negative 5 over 3. That actually would be a little bit better, wouldn't it? If you put a decimal past each of those, and that gives you 10 over 6, that'd be negative 5 over 3. That'll be a lot easier to deal with, I think, later. So now we're going back to fractions, I think. I'm not certain this is going to help us, but I think it will. Negative 5/3. Okay. And our new bottom row is 0.7, 0.7, 0.9, negative 1.1, 1, and 0. Okay. Now, what do we want to happen next? 0 above and below it. Okay? So how can we get a 0 on the first row? Times row 2 plus row 1 is the new row 1. Okay? Who said 3 by 3s were easy? Okay, not I. Okay. First entry, let me write down the second row. 0, 1, 2, 2, 0, negative 5/3. Okay? So new entry on row 1. 1, that didn't change. Next. Zero. Okay, now's the time maybe for your calculator. Negative 2.3 times 2 will be a negative 4.6 plus 2.1. Negative 4.6 plus 2.1 will be negative 2.5. Is that right? Okay. And then the next one, it's ugly writing up there. Negative 2.3 times 2 is again negative 4.6 plus 0.1 will be negative 4.5, right? And next will be, I'll do that one, 0. Now we got a mess, a real mess on our hand. So do it however you want to. Negative 2.3 times a negative 5/3. That's going to give you a weird number. It's going to be positive, but what's it going to be? Negative. Let's see. Let's call that negative 2.3. That would be negative 23/10. Okay. Plus okay. Yeah, negative 2.3 times 5/3, negative 5/3. Second? 2.83? Okay. 2 or 3, I can't hear it well. 3.83. Okay. Now you could call that 3 and 5/6, I think, but we'll let it go like that for now. Okay. Now we got to fix that bottom row too. This time you're multiplying negative 0.7 times row 2 and adding it to row 3 for the new row 3. So the first stays a 0, thank goodness. The next one becomes a 0, thank goodness. The next one. Negative 0.7 times 2 is negative 1.4 plus 0.9. That's 0.5, negative 0.5, right? You did, okay. I'm doing it in my head, and my head is not very good sometimes. Yeah, negative 0.7 times 2 is negative 1.4 plus 0.9 is negative 0.5, I think. Okay. Wait. Yeah. Okay. Then negative 0.7 times 2 again is negative 1.4 minus 1.1, and that would be a minus 2.5. Is that right? Okay. Next is minus 0 plus 1 is 1. I can do that one. And the next, this one really stinks. Here's, oh no, it's, well, it still stinks. Okay. That gives me a positive 35/3, I believe. So 35/3. I think I'm just going to leave it like that. 35/3. Okay. The previous was a minus 5/3, and this one up top, that's 3 and 5/6. That would be 18 and all right, we're going to leave off, yeah. Negative 18 plus 5 is negative, no, is, yeah, negative, no. Positive 23/6, I believe that is. Let me see if that's right. My brain's not working too well. Yeah, I think that's right. 23/6. Okay, what are we going to do now? Multiply this by -2. That'll make it a 1, right? Okay. So multiply row 3 by -2. -2 row 3 is the new row 3. Now I need to put it somewhere. So, unless I made a stupid mistake, I'm going to go on and erase the stuff at the top. Is that okay? I hope this won't hurt too badly. Okay. Yeah, I think I'll take that out too. And may even take this out as well, because that's what we're gunning for. AB inverse. Alright, we've got an AB, now we're working on the inverse. So let's go up here for our new matrix. And we're going to multiply row 3 by -2. So it'll be a 0, a 0, a 1, a 5, a 1, and that's a -70/3. I think. Okay. Ugh. Now, I guess I need to write these two in. Or, is it, all right, let me just do it this way. 0, 0, 1, 5. I think I messed something up there. That should be a -2 here, shouldn't it? And -70/3. Okay. Am I right? Yeah, I think I am. I don't know how I messed that one up. Okay. That's now new. Okay. So I've done this. So now what we're going to do is clean up here. So here we're going to multiply 2.5 times row 3 plus row 1 is the new row 1. Alright. This is a -2 here, I believe. Okay. Just looking at something here, that should be a 7/3, not a 70/3. And I'm not sure how I did that. But that, looking at their answer, is a -7/3. And let me go on and delete that before we bite something else up in so doing. Okay. Now I have to go back and figure out how I messed that up. And I may have erased too much to do that. Oh yes. I was multiplying 0.7 times 5 and I did 35 and it should have been 3.5. So yeah, that is correct. Whew, I thought that's way too big. All right, so now we're going to do 2.5 times row 3 and add it to row 1. That stays a 1, that stays a 0, and this becomes a 0. It has to. Okay. Now, 2.5 times 5 is 12.5. Okay. Minus 4.5, I think is 8, isn't it? Yes. Okay. And 2.5 times minus 2 is a 5, plus 0 is 5. And this one stinks. 2.5 times negative 7/3. Unfortunately, they'll be right in making, okay. So let's see what we got then. 2.5 times minus 7/3. Oh man, that's going to be minus 12, no. Negative 17. Goodness, this is too soon after lunch to be thinking this hard. Okay. 2.5 times negative 7/3 is going to be minus 17.5 over 3. Okay. And we're going to add to that 23/6, which will, let's make this minus 34/6, right? No, 35/6. Minus 35/6 plus 23/6. That's going to be 12/6. Can it come out that nicely? Minus 2. Yes, it did. Wow. Did you see what happened there? Okay. Goodness gracious. I hate fractions and decimals mixed together. It's so confusing. All right. Row 2. That's going to be much easier. Negative 2 times row 3 plus row 2 is the new row 2. All right. So that'll be minus 2 times 0 plus 0 is 0. Minus 2 times 0 plus 1 is 1. Minus 2 times that plus 2 is 0. Minus 2 times 5 is minus 10 plus 2 is minus 8. And that's what they got. Good for them. And then minus 2 times minus 2 is plus 4. And that's just going to be a 4. Good deal. And that last one is going to be 14/3 minus 5/3. 14 minus 5 is 9/3, which is a 3. And look at that. We've got the same thing they did. Here is the inverse of that. AB inverse will be this matrix here. 8, 5, negative 2, negative 8, 4, 3, and 5, negative 2, negative 7/3. And that's what we got. Now, if we go back and look, multiplying first did give us some pretty big numbers, okay? But we dealt with them okay, using decimals a lot, every now and then a fraction if we had to. And then undoing that gave us that. if you look in the book, they did the inverses first. They didn't show you how they did them, but they did them, and they came out without decimals or fractions, okay? Now, that doesn't mean you didn't have them in beforehand, but they came out without decimals or fractions, okay? And then no, B did. B had 2 fractions in it. So I think the way we did it is probably just as good, if not better than the other. Yeah. All right. Now, remember when we said any old matrices, A times C, if that's equal to B times C, that doesn't guarantee A is equal to B. In general, it's not. You can't cancel out matrices. But if they're invertible matrices, let's see what we can do. And that's what theorem 210 is. All right to erase? Okay. If C is an invertible matrix, okay, which means, of course, it's square, and, of course, it has an inverse, then the following hold. Okay, if C is invertible, 1. If, I can't write, if AC is equal to BC, now this says A is equal to B. If C is invertible, that's got to be true. Before, when we did these, if you go back and find that example, you'll find that C was not invertible. Or the sizes could be bad, or something else like that. Okay? And number 2, if CA is equal to CB, that implies A is equal to B. Okay? Whichever way you happen to go, right cancellation or left cancellation. Okay? Now, let's take the first one, AC equal BC. Okay? First thing we're going to do is multiply both sides by C inverse. Because C is invertible, so it has to have an inverse. So we know that's true. And what do you get? A times I equal B times I, and that gives you A is equal to B. So yeah, they've got to be the same. This is the conclusion there. We can do the same thing for this one, but this time we multiply by C inverse in front, and we'll get the same results. Okay. Those proofs, I don't mind. They're pretty easy. And they use almost similar techniques. Okay. Now, be sure to remember this theorem can only be applied if C is invertible. If C isn't, don't even think that A could equal to B. Example 5 in section 2.2 gave an example where that wasn't the case, and that's because C was not invertible in that problem. Okay. Now, did I bring up my watch? I get carried away sometimes, so how are we doing on time? Oh, we got a little bit. Okay. Now let's look at systems of equations. Okay. So I'm going to erase what's on here. Is that all right? Okay. For square systems, those having the same number of equations as variables, you can use the following theorem to determine whether the system has a unique solution. Okay? So if A is invertible, of course that means it's got to be square. Okay? An invertible matrix. Okay? Then, the system of linear equations, A times the vector x equal the vector b, okay, where those have to be appropriately sized, has a unique solution and that solution is given by x is equal to A inverse times B. Okay? If A has an inverse, that system's going to have a solution, and that's what the solution is. A inverse times B. And you can prove this if you can multiply by A inverse both sides. And then these become the identity matrix, and that times the x thing will just give you x. So sure enough, that will be the case. They go into uniqueness as well, but we won't mess with that. One use of that theorem is in solving several systems that have the same coefficient matrix. Okay? You could find the inverse matrix once and solve each system by computing that. Okay? So, here's basically what they're saying. If you're trying to solve this, and that's all you're trying to do, use Gauss elimination. It's much faster than finding the inverse of A and then multiply by that. Okay? Well, a 2 by 2 would be pretty easy, but that can be solved pretty easily anyway. Okay. So, this doesn't look like it makes a lot of sense. Unless you, and remember, oh no, that was in the other course. If you're shooting for something, okay, and saying, well, what would happen if we did this or did this? And this was the same thing, and you're just trying out different B's to see the final result, but this matrix was the same, then Gauss elimination, you'd have to do it for every one, because once you change the B, you have to go through the whole process again. But if you're doing it repeatedly, then do this one once. Find the inverse once. And then that's a simple multiplication because it's, n by n, n by 1. Okay? So and you got it done. And that gives you the thing. So if you're doing repeated and you're trying for different B's, do one inverse matrix and then just do the simple multiplication. Otherwise, you got to do Gauss elimination on every different choice of B you have. So that's where it comes in handy. Okay? If you're doing several systems at once. Okay? So let's clear the screen and do what it says. I'm going to cheat on this. 2x plus 3y plus z is equal to 1. 3x plus 3y plus z is equal to 1. Now that first one was a minus 1, sorry. I can't read. 2x plus 4y plus z is equal to minus 2. Okay? And then if you look at the B one, look at those coefficients. Identical. Okay? So the next one is just going to be a 4, 8, 5. And then look at the third one. Identical coefficients. Blah, blah, blah. Blah, 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 blah. And then you get 0, 0, 0. Okay? Guess what? I can answer, well, okay. Les, where would you begin on this? Would you do Gauss elimination? No. On this one, since you're repeating it, let's do one coefficient matrix, find its inverse, and then do. So the coefficient matrix is okay, and then we'll do our augment that with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now, if this were a little bit later in the course, I'd be real tempted to change the order of my variables and put the z's in front and go from there. You just have to keep up with the fact that you've done that. But we're not going to do that now. How would you proceed here? Negative of the third row to the, wait.
Take the negative first row
Yeah,
and add it to the second row.
okay. So you'll make a 0 there where the 3 was. On the second row or first row?
If you used to do what I just said, you'll have 1, 0, 0 for that first.
Oh, gotcha. Okay, got it. And make, if I'm understanding what you're saying, the negative row 1 plus row 2 will become the new row 1. Okay, I got what you're saying now. So let's do that. Good choice. Okay, so we're changing row 1, and it becomes what's that?
I was actually changing row 2.
Changing row 2. Oh, and then you're going to flip them?
Yeah.
Okay, we could do that. Well, that's sort of what I'm doing. Yeah. Okay, but yeah, let's do it the way you said. That's exactly what I'm doing. I'm flipping at the same time. It becomes the new row 1, not row 2. So that would be what? Ooh, yeah, it is. Yeah, it is. And that would be a 0. Yeah, negative 1, 1, 0. Okay. Now the question is, what goes next? Is that should be the top row or the second row? I guess it should be the new row 2. Yeah. 2, 3, 1, 1, 0, 0. Is that what you said? And then this is 2, 4, 1, 0, 0, 1. Okay. We'll do it that way. Okay, they don't show any of their work. Okay, I didn't realize that. They don't show a bit of their work. Okay, they just said it becomes this. All right, what's next? Okay, yeah. Yeah, probably so. I was real tempted to do the same thing you did down here, but that probably would be stepping out too soon. or would it? If you did minus row 2 plus row 3, want to do that? Minus row 2 plus row 3 becomes the new row 2. All right. So let's see what that becomes. Let's see if we can squeeze it in here. 1, 0, 0, minus 1, 1, 0. Yeah. Okay. And the new row 2 would then be 0, 1, 0, negative 1, 0, is it 0? Right? Is that right? Okay. Now the question is, what is our new row 3? Is it the old row 2? I think so. So that would be a 2, 3, 1, 1, 0, 0. All right. So now all we have to do is clean up that first entry, right? So that will be minus 2 row 3 plus row 1, no, row 1 plus row 3 is the new row 3, right? Wrote them backwards. Okay. So we leave the top row alone, 1, 0, 0, negative 1, 1, 0, and 0, 1, 0, negative 1, 0, 1. And now the new row 3 will be 0, 3, 1, 3, negative 2, and 0. All right. Now using row 2, we'll do negative 3, row 2 plus row 3 is the new row 3. Okay? So we're going to leave the top 2 alone. 1, 0, 0, negative 1, 1, 0. How are we doing on time? Oh, my goodness, we're out of time. I'm sorry. These things always take longer than you think. Think you can wrap that up at home? All right. See what you get. And then are you going to multiply it by the B's and see what you get? I'll tell you what the third one will be. 0, 0, 0. Okay, there's no choice. It's an invertible matrix. It's only have one solution. The only one that'll be is the thing. So homework exercises here would be any of the odds, 1 through 5. They're all at Calc Chat. They're in the back of the book too, and at Calc Chat. At Calc Chat, you have worked out solutions. Any of the odds 7 through 29. There's a whole bunch of those. Any of the odds 31 to 35. Either 37 or 39, and then either 41 or 43, 47 or 5 or 47. They're all at Calc Chat. 49 or 51. My word, that's getting long. Okay, and then 53, 55, 57, 59. Okay, 61. And now they're talking about a brand new thing called the flexibility matrix and blah, blah, blah. And then there's a true-false 63. Okay? There's a proof. Well, here are some proofs. 65, 67, 69, 71. Okay? Any of the odds, 65 to 71, are proofs. You can do those if you'd like. Writing, in other words, think through some of these. 73. 75 is one you can actually work, and 77 is a proof, and it's called the householder matrix. Haven't quite figured out why. 79 is something you can work. 81's a writing, and 83, so you can choose to do either one of those. Ready to get started on 2.4 next time? Okay. I hope I find my stuff before then, or else I'm not going to be a happy camper. All right.